Thanks very much, Tom. Can you hear me okay? How's my volume? All right? Okay. Well, thanks very much for coming. It's really nice to see such a big crowd here tonight, and I'm really pleased and grateful that you all come out to hear me talk about this. Actually, the title of this talk actually raised some questions. I got an email from one of my colleagues here at Stewart Observatory the other day saying, "You know, Ed, I didn't think that there were any hazardous asteroids on Mount Lemmon." And if there were, it'd be very easy to find them. So what's so difficult about it? And I said, well, of course, the grammar is wrong. So I played with the title just a little bit. And I came up with that, but that sounded a little stilted. So I thought that maybe I would take sort of the Edward R. Murrow approach and say from Mount Lemmon. But then I thought, to heck with it. Let's just put it where it ought to be. So what we're looking at right here is our 60-inch telescope up on Mount Lemmon. This image was taken by Richard Kowalski, who's one of our observers, and he's also a talented photographer. If you watch Channel 13 at night, oftentimes you'll see a few of his photographs there too. But we're here to talk about asteroids tonight. And so the question is, first of all, what are they? Well, they look like rocks, but they're not just rocks. They're not just boulders. We've actually had the opportunity to fly by them with some spacecraft and image them. And you see one here. It looks kind of ominous floating out there in space. About 15 or so of the asteroids that we know about are over 100 miles in diameter. The rest of them are smaller than that. Most are less than 1,000 feet across. But we believe that asteroids weren't formed this way, the way we see them right here. We believe that they were actually part of a larger parent body at some point, and then were broken up by some sort of force, either through collisions or gravitational interactions with the large planet Jupiter, and perhaps in some possibilities with Saturn. They continue to interact with each other through collisions and gravity, and those interactions can be quite complex at times. Where do we find most of the asteroids? Well, we find them in an area called the asteroid belt. And what we've got is we're looking down on the solar system here. So we've got the sun and the 4 terrestrial planets on the inside with the orbit of Mars right there at about, a little over, around 200 million miles. And then outside we have the asteroid belt. All these white objects are about 400,000 asteroids have been cataloged so far in the asteroid belt. We also have some things called asteroid families. Families share some sort of relationship either through collisional history or through their dynamic interaction with the gravity of Jupiter. So we see, in some cases, these green objects, we call these Trojans, and the Greeks, these are the 2 families, and they're there because of a complex gravitational interaction with the planet Jupiter. We also have these brown objects here called Hildas, and there are many, many other families that we find with asteroids. Now what we've got here is a simulation using all of the known asteroids as of about 2005. And we're showing the inner 4 planets right here. So there's the orbit of Mars. And on the outside is all of the main belt objects. And you'd think, how would we ever get a spacecraft through that? Well, these spots are actually much, much larger than they should be. We just can't make them small enough. They should be about 10,000 times smaller than we can actually make them here. So the upshot is that even though there's about 400,000 asteroids out there, we have no problems getting through them with spacecraft. Now, the white and red objects that you see on the inside of the solar system, those are the ones we're really concerned about. We call some of these, especially the ones in red, near-Earth objects. Any asteroid that comes within about 125 million miles of the sun also comes relatively close from time to time to the Earth or one of the interterrestrial planets, and could, through a gravitational interaction, become perturbed. Its orbit could be changed. And that changed orbit could cause it at some point in the future to intersect the orbit of the Earth, and that would be bad. So that's what we're all interested in knowing about, are these near-Earth objects. So we also see that all the meteors that we find here on the Earth were near-Earth objects at one point in the past. This is a picture, a video of an object that came down over the northeastern part of the United States. I believe it was 1992, and landed in northeastern part of the United States, Peekskill, New York. And it actually was seen by thousands of people. It shows the track here coming across the United States. And it landed actually on the trunk of a car. So that Chevy Malibu is worth a whole lot more now than it was brand new. And it's actually a lot better traveled than I am, too. Some guy bought the car and the asteroid, or the meteorite, and he travels all over the world with it, showing it to folks. But this happens all the time. That teak scale object was just probably a few feet across, didn't really represent any threat. This was what most asteroids end up being when they come into the atmosphere, is something quite small and nothing to worry about. But then we start to look at other places around the solar system, like the moon. And if we just had to worry about these small objects, we wouldn't have to worry much. But look at the moon. How did it get that way? It's apparently been peppered with asteroidal impacts over the last 4 billion years or so of its life. We know that the rate of impact has decreased over time, but hasn't stopped completely. Have meteors hit Earth before? Should we be worried? What is the threat? Well, if we take a look at one meteor crater right here in the state of Arizona, this guy is a mile across and it's 1,000 feet deep. And it was made by an object about 50 meters across, 150 feet or so. It was actually created by a nickel-iron meteorite that hit the Earth about 50,000 years ago. And nickel-iron meteors are actually much stronger. There's about 10% of all the meteors that come into the atmosphere are made of nickel and iron, very strong metal. Most of them are made of stone. So most of the objects around 50 feet or less in diameter would break up when they hit the atmosphere because they come in at like 12 kilometers per second. That's 25,000 miles an hour. So hitting the atmosphere is like hitting a brick wall for one of these things. But nevertheless, we do find these things. And the object that made this is called the Canyon Diablo meteorite. And if you go to the gem show, you can actually buy a little piece of it for less than $100. But there are bigger ones. This monster is the Manicouagan impact structure in northern Ontario. Originally, it was about 62 miles across. And because the Earth has an atmosphere, it rains, water moves across the Earth, that all conspires to erase the evidence of these impacts from long, long ago. This impact happened about 215 million years ago. And it was created by a 3-mile wide asteroid that hit the Earth. Again, at about 12 to 15 kilometers per second. So we have to start looking around, and when we start doing that, we see that these kinds of structures are to be found all over the Earth. We can actually find many, many instances of very large impact structures in the Earth. And we only have 1/3 of the Earth as land area. So we can figure that there's been many of them that have hit the ocean that we don't have any evidence for, that evidence is much more difficult to get. But there's one crater, one event that requires some special attention. About 65 million years ago, in an area near the Yucatan Peninsula, an object hit about 6 miles wide, hit the Earth, and threw up a tremendous amount of ash and soil into the atmosphere. We know this happened because we have found gravitational anomalies in the area where there's compressed soil and denser material. We found shocked rock that you only find in meteoritic impacts or in nuclear explosions. We find melted remnants called tektites that were dated to about 65 million years ago. And we found evidence for tidal waves around the entire loop of the Gulf of Mexico, tidal waves that were over 1,000 feet high. We've actually found soil or remnants from the bottom of an ocean well into the state of Texas that correlate very nicely with an impact 65 million years ago. So what would it have been like? Well, of course, we would have had these tsunamis, thousands of feet high. There would have been global wildfires caused by this. Earthquakes might have been induced. Superheated material would have been sprayed in the atmosphere by the hundreds of millions of tons and would not have come down for years. The effect of that would have been to change and break down the food chain. So if you weren't a small critter living in a hole somewhere, you were in trouble. And as a matter of fact, the current thinking right now is that the dinosaurs may well have been caused to go extinct by this impact. Now, this is somewhat disputed, but some people believe that maybe they just had a bad smoking habit. But generally, the feeling is that this was so well correlated with the disappearance of the dinosaurs that it's very likely that this could have been an extinction level event. So, how do we prevent another bad day from happening on Earth? Clearly, another event wouldn't help us out too much. I mean, it was good for us probably 65 million years ago because it got rid of the reptiles and maybe let us small mammals evolve into human beings. But I don't think we want to give the reptiles a chance to get the Earth back. So what are we going to do about that? Can we prevent it? Well, this man was one of the first people to really think about the problem. His name was Eugene Shoemaker, and he was an Arizona resident for many, many years. He was one of the first people to determine the meteor crater in northern Arizona was in fact a meteor crater and not a volcanic structure. He also pioneered the use of finding shocked rock as an indicator for impacts. But he also had started to look around the solar system. He looked at the moon, he looked at the inner planets, he found craters everywhere, and he thought, this could be a problem. And he knew that while the chance was slim, the consequences of an impact was great. And he began to advocate for search for these objects to see if we could find anything that would represent a threat to the Earth. So in the 80s, Gene Shoemaker, his wife Carolyn, and David Levy began a small photographic survey with the Palomar Observatory 18-inch Schmidt. And in the course of that survey, as all surveys do, they discovered a comet. And as comets are, they are named after the discoverers. It was called Comet Shoemaker-Levy. And this was in 1993. And what seems like a fantastic stroke of chance, Shoemaker-Levy 9 was determined in 1993 that it was going to hit Jupiter in 1994. And what had happened is in 1992, before it was discovered in an early pass of Jupiter, its orbit was perturbed in such a way that it was going to actually hit Jupiter the next time it came around. And what you see here is a loop of an infrared image of one of the components of Shoemaker-Levy hitting Jupiter with thousands of megatons of equivalent explosive force. Now what had happened is the gravitational force of Jupiter had actually broken Shoemaker-Levy up into 9 distinct pieces. So what we're seeing here is an impact, but we're also seeing the remnants of earlier impacts as Jupiter had rotated around. So in a freight train-like collision, Shoemaker-Levy 9 hit Jupiter and the whole world was watching. So this was really fantastic. This is the sort of thing we don't expect to see in our lifetimes. And this got the Congress attention. So we knew, we had Gene Shoemaker saying, we need to be looking for these things. We had evidence of an extinction level event 65 million years ago on the Earth. And then we turn around as we're having this conversation and we watch another planet get hammered by a comet. So the Congress said, we would like NASA to organize a search for these objects. We would like for you to see to it that we inventory 90% of the most dangerous of those objects, and that is the 1 kilometer size or larger objects. So with that was born the Space Guard Survey, informally named the Space Guard Survey, and that involves several observatories. 3 of them that are shown here. This is the linear program. It was a collaboration between the Air Force and the Massachusetts Institute of Technology. The NEAT survey, which used the 48-inch Ocean Schmidt at Mount Palomar, and our own sister survey at the Lunar Planetary Lab, Spacewatch, which was actually one of the very first NEO surveys to use electronic detectors searching for asteroids. Now, our own Catalina Sky Survey began in 1998, and we stopped for a while because we found that we really needed some equipment changes, some upgrades. Our specialty is taking disused telescopes and upgrading them and making them useful again. So we got a rather generous grant from NASA to upgrade several telescopes. The first one that we use that is really our most powerful telescope is the 1.5 meter telescope at Mount Lemmon. And here we've got this big shroud or curtain on it to get rid of stray light. But when I say 1.5 meter, does everybody know what I'm talking about when I say that? I'll give you just a short little tutorial here. At the base of every mirror is every telescope is a large mirror like this. Every telescope that we use. And it happens to be 1.5 meters in diameter. It's just like setting a bucket out in the rain. If you want to collect more water, you set out a bigger bucket. So light comes in through the top of the telescope and hits the mirror, is bounced up to a camera at the top of the telescope. The larger the mirror, the more light you can concentrate in a smaller area, the fainter objects you can see. So we use the 1.5 meter telescope at Mount Lemmon. We also use a 0.7 meter Schmidt camera, which is a sort of a variation. It's not so much a telescope as it is a camera. There is no place to look through on this instrument. There's a camera at about right here on the inside of the telescope. This has an advantage of having a very wide field of view. It's a wide-angle lens on the universe. We can actually see or cover the entire sky every month with this telescope. So it really sucks in a lot of sky in the process. But we can only see objects from Mount Bigelow and Mount Lemmon. We can only see objects in the northern hemisphere. So we need another survey in the southern hemisphere. And we have a 0.5 meter Schmidt telescope at Siding Spring, Australia, which is about 220 miles northwest of Sydney. Siding Spring is an extremely dark site. It's an established observatory site in Australia. And we're working in conjunction with the Australian National University. They're our partners in this process to conduct a survey from the southern hemisphere. So what we really have is we have kind of a triple threat. We've got our big telescope, which can go deep. It can find faint objects. We've got a 0.7 meter Schmidt, a wide-angle telescope that can really cover lots of sky, which is really the secret when you're trying to look for new asteroids. And we also have a wide-angle Schmidt in the southern hemisphere. So we really have got a very nice combination of non-overlapping capabilities with these three telescopes. Now, just recently, what we've received is a new grant from NASA and a matching grant from some private benefactors to put another telescope into service on top of Mount Lemmon. This is the 1 meter telescope, which has fallen into disuse. We received about $500,000 to refurbish it, but we're not going to be searching for asteroids with this telescope. We're actually going to be doing follow-up work, and I'll talk a little bit later about why follow-up is so important in doing this. So what we do is really pretty simple. If you wanted to watch something moving, a good way to deal with that, or the good way to find something that was moving really slow, like a turtle, you could just set a camera out and you could take a picture about every 10 minutes. And if you compared all the pictures, you'd notice that, while you might not see the turtle moving instantaneously, over 40 minutes you'd see he'd actually made a little progress. So what we do is we break the sky up into chunks of sky, predefined sizes that correspond to the field of view of each telescope. This happens to be the field of view of our Uppsala Schmidt telescope in Siding Spring, Australia. For those of you who are amateur astronomers, you may actually recognize Orion here. There's his belt, 3 stars, and his sword, shoulders, and his feet. So what we do is we set up a sequence of observations. We'll say, all right, I'm going to observe this field. I'll take a picture here, then I'll take a picture here, and I'll do this. And these exposures are 30 seconds long, and I'll maybe do this, and then I'll come back and I'll start over, and I'll do that 4 times. So for each one of those fields, I'll get an image spaced by about 10 minutes in time. So then what we do is we have a piece of software that can electronically register the images so that the fixed stars don't move. And then that software can go looking for objects that are moving in the field. Now, this happens to be a rather bright, already known object, but this is very representative of the sort of thing that you see if you happen to be observing at one of our observatories. The strategies that we employ for each telescope are kind of a function of where we happen to be, the capabilities of the telescope, where people have looked on previous nights. But the idea is we'll try to get as much coverage every month as possible, limited only by the weather. We observe every night for about 24, 25 nights a month, except for those few nights, 6 nights or so, around the full moon when the sky is just simply too bright to find faint asteroids. Now, what happens? It's not enough just to discover a new asteroid and call somebody up and say, there we go, we're all done. You've got to follow up on these things. And we don't really have a lot of time to do follow-up. And in fact, we've really relied on a very talented cadre of amateur astronomers to do our follow-up for us. In fact, one of them's here tonight. He's been, absolutely a powerhouse. in getting some of our observations followed up for us. And what we do is we report all of our observations to a site that's run by the Minor Planet Center, and they post a website called the NEO Confirmation page. And this happens to be the page from last night. And so these are all new objects that were discovered last night, and I'm proud to say every one of them are from our observatory. So this is very typical of the sort of thing that happens, and then amateurs and professionals all over the world watch this website, and then they go out and get additional observations. Because the idea is we're trying to determine orbits. We want to know the mathematical relationship that allows us to predict the position of an asteroid at any point in the future. And in order to do that, we need more than just those 4 discovery observations taken over 40 minutes of time. We need observations later that night. We need observations the next night. We need observations maybe a week from now. And in some cases, multiple observations into the future in order to really keep tabs on these objects. So follow-up is really, really important. And that's why we are developing a new follow-up telescope for our observatory, because we don't want to take our discovery telescopes, our survey telescopes that are optimized for search. We don't want to put those to work doing follow-up. That's why we are developing a specialized follow-up telescope to go after the really faint stuff that a lot of the amateurs can't help us with. So today, the Catalina Sky Survey is really the leader in discovery. We find about 70% of all the near-Earth objects. And this graph shows the discovery, the numbers of discovered objects for each 6-month period, starting at the end of 2008 and working its way back to 1995. The Catalina Sky Survey is the purple here. So you can see we're really walking away with it. But the thing that's interesting is you also see an increasing ramp of discovery. We're discovering more objects every year. And I think that's really a testimony to the efficiency, the efforts that we've made to try and make our program more efficient, to find more objects, fainter objects, make sure we don't lose objects, to work with our collaborators around the world to do a better job every year. So, does anybody have any idea what we're going to do if we find one of these things? Come on, somebody knows. Everybody asks me if we're going to do this. You get Bruce Willis. So, no, unfortunately we can't send Bruce Willis to do this. It's actually a little bit more complex. But we have thought a lot about what you do when you have an object that's been discovered that perhaps might represent a threat to the Earth. You have to answer a few questions before you can actually begin a serious mitigation effort. The first thing that you need to do is
turn your volume up.
Oh, okay.
So they can hear your laptop. You might want to play Bruce Willis again.
Oh, that's all right. He's not really saying much important.
Okay. Looked pretty fun.
Did anybody ever see that movie? It was an awful movie. But a lot of what we tend to do, or what we will do, is going to be determined by how much time we have to deal with these things and what the objects are like. Now, this is an image of an asteroid called Itokawa. It was taken several years ago by a Japanese spacecraft. And if you look carefully, you can see that it's not really one piece. We can probably make out what are 2 distinct pieces here easily, probably a third chunk, and then a bunch of dust that's probably gotten raised up as the objects have rubbed together a little bit over time. So if you go up and push on this thing, it may come apart on you. And in fact, we really don't know for sure what these guys are. They may be pieces or remnants as well. So how you actually go about dealing with it if it's going to hit the Earth really depends on how these things are put together. So that's something we would have to worry about. Now it's really important to note that our goal is to find these things very early if we can. It's not really a great thing to find out that we're going to be hit by an asteroid tomorrow. After all, you've just got through renewing that magazine subscription for the next 3 years. So our goal is to find these things very early, to get the orbits, to predict those orbits well in advance, and then try to find out whether there's something we should be doing. But dealing with this might be kind of hard, wouldn't it? But not actually, it would be hard, but not maybe as hard as we think. In July of 2005, we actually sent a space probe to a comet, which actually turns out to be very much like an asteroid, just covered with a lot of ice. And we sent it to the comet named Tempel 1. and we slammed into it with an 816-pound copper slug at over 6 miles per second. And there's a little time-lapse movie here of us actually, the spacecraft hitting, and we stood off and watched with another spacecraft. Now, this wasn't just a fun thing for a bunch of mad scientists to be doing. What this was an effort to do some geology. And the first thing a geologist does is he takes his rock hammer out and he hits something. And he hits it because he wants to see what's underneath that layer of external material. He wants to see some of that fresh rock. In this particular case, what the scientists who were involved in this experiment were doing were watching this debris that was blown out from the asteroid when this slug hit it. But the other thing that it demonstrated was the ability to actually station keep and hit something that's moving at a relative velocity of 6 kilometers per second. So in some ways, this was a technology demonstration of how we might go about actually hitting an asteroid. Now, in this particular case, we wouldn't probably, if it was an asteroid that was headed towards the Earth, we probably wouldn't use an 816 kilogram copper slug. We'd probably use an 816 kilogram uranium slug, a bomb. And what we actually think would be the right thing to do would not be to hit the asteroid directly, but to actually explode a nuclear weapon in the vicinity of the asteroid. Not to destroy the asteroid, but to nudge it out of the way. Consider if there was an archer at the back of the room and he was going to shoot his arrow towards me. If somebody could just step in his way and nudge the arrow just a little bit, way back in the back, the arrow might hit way over here. So all we have to do is push these guys along just a little bit, using something like a nuclear explosion or some other techniques early enough on. If we can do that early enough, then we could probably make an asteroid miss pretty cleanly. It's all about having enough warning. Now there's a couple of other ways that have been discussed in dealing with asteroids that might hit. One's called the gravity tug. A gravity tug is actually just a spacecraft that positions itself close to the asteroid. The spacecraft is kind of heavy, not nearly as heavy as the asteroid in some cases, but by just station keeping next to the asteroid, the gravitational attraction between the asteroid and the spacecraft could slowly nudge the asteroid out of the way. You'd have to have some time for that, but that might be a very elegant, highly controllable kind of situation. We could use something like that 816 kilogram copper slug, except that maybe we could hit it at 30 kilometers a second, and then we could do it maybe 15, 20, 30, 40 times, so we could have a sort of an interstellar pea shooter that would knock this thing out of the way. And there's been some other ideas that include things like just painting it white, because sunlight actually exerts pressure on things. Given enough time, if we were to paint an object with white paint, that might provide just enough added efficiency in the sunlight pushing on the object that it could actually nudge it out of the way over a long period of time. And I'm sure that you could get sidelets to do that for nothing if they could just have the marketing rights on moving the asteroid. Anyway, there's various ways that have been discussed to do this. Whoops. So I would like to tell you just a little bit about two asteroids that we discovered in the last 6 months or so. One's called 2008 TC3. You might have heard about it. It actually landed in the Sudan in October. And that was one of our discoveries. Rich Kowalski, the guy who took the picture on the front of the slide, was observing on October 6th at about 11:39 at night, and with our 1.5 meter telescope on Mount Lemmon. And he discovered this little object moving at about 2.5 degrees per day. Let's see here. Is it moving? I guess we don't have the animated. So it was fairly bright. He reported it to the Minor Planet Center immediately, and he started up with some follow-up images about 90 minutes later. And also one of our Tucson amateur astronomers who do the follow-up was also on the object that night. So by the time the morning came around, there were several observations of this thing. Let's see here. Stop. There we go. Okay. So the Minor Planet Center made a preliminary analysis of the orbit of this thing, and they said this is going to hit, and it's going to hit in about 17 hours. Now, wait a second, Ed. You said you were trying to find these things way in advance. Well, it turns out this guy was only about 2 meters in diameter. He was relatively small, He was discovered at about 350,000 miles away. That's farther than the distance of the moon. It was moving pretty quickly, but the process by which we went to determine how this object was going to hit and where it was going to hit was fascinating, and it worked out really well as a demonstration of the capabilities of the system that we have in place. The observations were made public to allow confirmation of all the computations. There's actually 3 major centers around the world that compute orbits for asteroids. They use different techniques to make sure that they're right. They compare the results with each other. The NASA JPL NEO program office was alerted, NASA headquarters was called up, and the object was given its little cryptic designation 2008 TC3. There also happens to be a small group of amateurs who compute orbits. And it's this fellow by the name of Bill Gray, a really talented fellow, also came out that morning and quickly said, this thing's going to hit the Earth later this afternoon. So about an hour after the Minor Planet Center said this thing's going to hit, the Jet Propulsion Laboratory also did a series of computations which said this thing's going to come down over North Africa. And it's going to probably land in the Sudan at around 7:46 on the night of the 7th. So we started, we're just the observers. We just kind of sit back and watch the wheels grind after this sort of thing starts. But the National Security Council and several other responsible agencies were notified because this thing was going to actually explode with about a kiloton of equivalent energy in the upper atmosphere. If you happen to be a small country who felt threatened by another country nearby that happened to have nuclear weapons, this could be improperly interpreted as a aggressive act. So we actually have some processes in place within this country to notify smaller countries to let them know that this is expected and that it is not a man-made explosion. And then NASA finally issued a press release at about 2:30 on the 7th of October. Here you see the trajectory of the object as it came in just prior to its impact with the Earth. Now, in the time from the time that we discovered it to the time it hit, about 20 hours total, there were 570 observations made by 26 amateurs, I think it was, and professional and amateur observers. They determined it was about 2 to 3 meters in diameter, moving about 12 kilometers a second, and it probably was going to have about a kiloton of energy associated with it. One amateur put together a movie of this object moving past, and you can actually see it varying in brightness. And that indicates the object is not rotating uniformly, but it was tumbling. There was also an opportunity to get spectra. Now, if those of you who come to the Stewart Public Evenings probably know what spectra are, but spectra is a technique. Getting a spectrum of an object is a technique for actually determining composition. So there was actually some initial work, there was time to actually get composition studies on this object. Now, northern Sudan is not a great place to be if you're just walking around in the desert. It's an area where there's been a lot of conflict. We didn't have much time, so we couldn't really get people in place to watch the entry. But there were several people, several agencies that were able to confirm this, including an airline pilot, an acoustic monitoring station that actually listens for airbursts for nuclear tests. There was a webcam at a Nile beach resort that at the right time of the morning showed a flash coming from the right direction. It was just a webcam. A European weather satellite actually saw a fireball in the infrared, and the US military issued a very terse 2-line sentence that said, "We saw it." So, and it turns out there was a group there from in the northern Sudan that from the University of Khartoum, who actually didn't get a picture of it coming in, but they saw the trail that was left in the upper atmosphere as the upper level winds began to run at different directions and to break that trail apart into different pieces. Now, this is the thing that's really cool. About a week and a half ago, they found a piece of it, they think. And this is the equivalent of the trifecta, because we got to see the object coming in from the moon, we got to see it entering the atmosphere, and we're going to get to pick it up and study it. So what that means is we can finally, this could effectively be like the meteor Rosetta Stone, because it will tie together observations of objects in space with laboratory observations of the same object. So we'll be able to relate what we see in observations where we don't get to touch the object to actually something that we've touched. That's extremely important. So we're waiting for confirmation. The way we'll confirm this is radionuclide studies of the asteroid, because there will be very short-lived radioactive elements in this asteroid that if it had been sitting on the ground for more than a year would have completely disappeared. So we'll know pretty soon. There's rumors that there's going to be a paper in Nature here pretty quickly saying what this is all about. So we're all looking forward to that information.
Question on that last picture.
Uh-huh.
What are they pointing at?
Well, actually, it's right down here, and I might have cut it off. So but you can see this thing is, you can see the size of the grains next to it. It's not very big. It's probably the size of a marble, a little bit larger than, a big marble. Can you imagine looking through the Sudan for that? You got to be really dedicated. Now, one other quick point I wanted to make is that just a few days ago, another object was discovered by our Siding Spring survey. This is 2008 DD45, another one of those great names. This little object was passed by last night at just 40,000 miles. That's about twice the distance that weather satellites orbit at. And it's about 100 feet across, and last night when it was observed by our Siding Spring observers, it was moving at 646 degrees per day. The full moon is a half degree across. The sky is 360 degrees around. So it was a very short amount of time it was moving that fast, but it was really hauling. And if you can see it right there, I'm sorry I didn't have a chance to put a marker on this. I put this together today just before the talk. But there's the discovery image of this object. The point is, this happens all the time. We find these objects flying by very frequently. But of course, the ones that we're looking for are the big ones. We have found none so far that we're really too terribly concerned about. There will be one that flies by the Earth in several years named Apophis. We'll all be interested to see how it interacts with the Earth and how its future orbit might be affected, but we know that it's not going to hit during its next pass. So that's our job. That's what we do. I'll leave you with a little time-lapse image of that Rich Kowalski took of our observatory working through one evening from sunset to sunrise. And I'll just leave you with a thought that for 24 nights a month, 3 people from the Lunar and Planetary Lab are sitting up on top of a mountain looking for these objects. It's tough work. It takes you away from your family, but they are very pleased to be able to do it. Just as I am very pleased to have been able to tell you a little bit about it tonight. So thank you very much, and if anybody has any questions, I'll be glad to answer them.
Thank you, Ed. By the way, I have to make note that on the night that asteroid hit over the Sudan, I was giving a public evening lecture right here in this very room, and I stopped the lecture to note to everyone at the exact time that it was hitting.
Did you hear the thud? Right.
Yeah. All right, we have plenty of time for questions. Yes?
Could you go back to that bar chart for a second?
Sure. Let's see if I can get that for you. Probably just do this here. That one?
Right, so the last 2 bars on the right-hand side.
Yes.
For 2008, whatever.
That's right.
Why is the second to last one higher? Were there more that they thought existed and then they were demoted?
No, these are actually the ones that we found. And so you'll see like weather cycles and so forth. Some years we have really lousy weather. So this is just the number of objects that were discovered by us.
For that year.
For that 6-month period. There's 6 months. So this is the first 6 months of 2008, second 6 months of 2008. Mm-hmm. Yeah. Yes, sir.
Yes.
What about objects that come from behind the sun? How much time does that give us?
Well, actually, there is a class of objects that we look for. We call them interior objects. So they're objects that are orbiting entirely within the orbit of the Earth, sort of like Venus or Mercury. Now think about when you see Venus. You never see Venus at midnight. You always see it early in the evening or early in the morning. And those interior objects would be also, those large objects that are orbiting the interior of the Earth would behave similarly. So they can only be observed for a few hours in the early evening, a few hours in the morning. Those objects we worry about. First of all, because they're hard to find. And they move fairly quickly. So they are observable for only a few days or weeks, and then they're not observable anymore because they go into the glare of the sun. So while I wouldn't say they come directly from behind the sun, they orbit interior to the orbit of the Earth, and that makes them difficult to observe, difficult to discover, and that's why we worry about them, because it's a lot easier to find objects that are outside the orbit of the Earth. Does that answer your question okay?
Yes.
Since we know so much about Apophis, where it's going to be
2026, I think it is, yeah.
is there some guesswork as to what our orbit or our mass will be with
There's, I referenced a fact that there's going to be an asteroid come by in a few years. You might have heard about Apophis. Apophis was discovered by another survey, a specialized survey at Kitt Peak, and then it was lost. And then it was picked up by our survey at Siding Spring a few months later. The two sets of observations were connected, and people started sitting back and thinking, wow, this is going to hit. And this is a 300-meter object, so it's pretty good size. So that really threw the entire NEO survey industry into high gear. And we started taking a lot of observations. We pulled in the planetary radar system at Arecibo to get some very high precision observations of the object. Radar, effectively, that gives you range information. That can help you nail the orbit right down. And we determined that, to the best of our knowledge, this is not going to hit in 2026. But believe it or not, it's coming by on Friday the 13th. And I believe it's April of 2026. And in fact, it'll come closer than communication satellites. It'll come in under 20,000 miles. So if you actually go to Europe and the weather happens to be clear, you'll be able to watch Apophis fly by with your naked eye. Now, the thing that scientists are worried about is that it's going to come so close to the Earth, its orbit is clearly going to be highly perturbed by that interaction. And it's difficult to know exactly how that perturbation is going to affect its orbit such that perhaps it might impact on another pass. What we work with as scientists is errors. So we have an error ellipse that this object can fly through. And we know that if it flies outside that ellipse, there's no problem. And the chances of it flying outside of that ellipse are very good. The chance of it coming inside that ellipse is about like 1 in 46,000. And if it does, it may represent a threat in a subsequent pass. So we're going to continue to watch Apophis very closely. But we can't say with exactitude where these things are going to be because the nature of these gravitational interactions are subject to some degree of error. So we will be watching Apophis. We're frankly not terribly concerned. We're more excited about it, but we will be watching it closely. I think it's like 12 or 14 years later. So 2026 plus whatever that is.
A question here, yes.
Yeah, approximately on the larger objects, how many orbits ahead can you predict?
It's probably not so much a matter of how many orbits, but how much time. We feel that our orbits are generally good predictors in most cases for up to 100 years. Beyond that, here's the story with NEOs. I mean, how did NEOs get here? It turns out NEOs don't have a very long lifetime as astronomy issues go. They only live for about 1 million years before one of three things happens. They hit a planet, they fall into the sun, or they get thrown out of the solar system. That's because if you're messing around in the interior of the solar system, you're going to have a close interaction with a planet, and it's going to perturb the object. It's going to throw it, it's going to change the orbit. And it's going to change the orbit in one of those three ways ultimately. So the real issue is we don't really know for sure how much time we have because they are going to get perturbed. And we think about 100 years as mean about how good these orbits are good for. That's why we have to keep an eye on them. Those objects that we call potentially hazardous asteroids, those are the ones that do come close to the Earth. They will continue to be watched from now forward. They've been identified, we keep an eye on them, and as soon as one happens to look like it might become a threat, then we'll notify the national security interest to see if we can do something about it.
There was a question over here. Yes.
So who writes the multi-body code for everybody? Does NASA give you something that needs to be right, or everybody write their own?
Well, actually, everybody writes their...
repeat that question.
Yes, okay, so he asked, who writes the software that calculates the orbits for these things? And it turns out there are 3 agencies in the world that we really look to do a lot of this work. One's at the Minor Planet Center. It's run by the Smithsonian, the collaboration of the Smithsonian and Harvard University. Jet Propulsion Laboratory, those guys are really good because they're the ones who figure out how to put a spacecraft on Mars. So they've got some really excellent codes for this. And then we also have collaborators in Italy. There happens to be some very, very sharp people in Italy who've written these codes. We actually feel that by allowing everybody to write their own codes and then compare the results is a better way to make sure that you don't have institutional problems inside the code. It's kind of like the space shuttle. It's got 5 computers on it, but one of the computers is programmed by a different company. And it's programmed to do things a little differently. They use their own algorithms, and the computers then vote. So if there's a problem, if there's an issue that comes up, that they come up with different answers, it can alert the pilots, and they can make a decision about what the right thing to do is. So this is the kind of the way this system works as well. We actually, and then I mentioned amateurs. Bill Gray, this amateur. He's got a piece of code, freeware. You can download it from the web. It's called OrbFit. Right? I think it's OrbFit. And you can download and pull the observations that we take, because they're placed on the Minor Planet Center webpage every night, and do your own orbital calculations. And it works great. It does a great job.
There's a question up here. Yes.
Yeah, referring back to the impact over the Yucatan, meaning using it, was it of such intensity that theoretically it could also eject material from the Earth so that it escapes the Earth's gravity into planetary space and create its own debris?
I think that's probably highly likely. I mean, when you have impact velocities in excess of 12 kilometers a second, it's very likely that some of the fragments, some of the material that's thrown off would be thrown off at a rate that's higher than the escape velocity of the Earth. So it's very likely. Material has been found all over the planet Earth from this impact. In fact, one of the smoking guns, if you will, of the Chicxulub impact, as it's called, is a thin layer of iridium that's found everywhere around the Earth at a level down in the stratigraphic column that corresponds to about 65 million years ago. Turns out iridium's rather rare on the Earth, but it's rather common in asteroids. So this stuff got splayed all over the planet, and we find it almost everywhere we look. I would bet dollars to donuts that you could probably find components of the Chicxulub impact on the moon. Yeah.
Yes.
NASA sorts these objects based upon the Palermo scale.
Yes. That's right. This is a scale. There was an attempt. There was a couple of events early on in the process. He asked about something called the Palermo scale. And there was a couple of events early on where we got some scares. And they were trying to figure out how to communicate to the general public the threat of one of these objects if it was coming close. And so they came up with a scale. There's actually 2 scales that are used. One's Torino and one's Palermo. The Italian, that's because of our Italian collaborators that do a lot of this kind of work, to try and quantify the threat. And it was like 0 is no threat and 5 is like run for the hills. And but there's been a lot of criticism level with those scales. And I'll be honest with you, I haven't really followed that criticism myself. The Apophis object came up to a threat level of 1 before the latest observations were obtained that pretty much took it off the list. So it's back down, I believe, now to something under 1. I think that my guess is that's going to fall into disuse. Because I don't think it really does the job that it was intended to do, which is to really inform the public about the threat level of these things.
James.
You didn't address it, but I think I will.
Okay.
The issue is that unfortunately a lot of people watch science fiction movies and don't have a good concept of the fact that if we do discover one that's big and it's going to hit the Earth, basically there's nothing to do about it. Because technology doesn't exist today to do anything. And it would probably take on the order of 10 to 20 years to even develop the technology once you decided you actually wanted to try to do something. So if anything hits the Earth in less than basically a 10 or 20 year window, there's nothing you can do about it anyway.
Well, I think there are people who would give you a credible argument opposite to that. I mean, there's a lot of debate about how well prepared we are. And certainly, I don't think we're necessarily prepared for all comers. But I've also sat and listened to people from Los Alamos who gave us, some fairly comprehensive information about nuclear weapons effects and how they might be used, and came up with some credible physics to suggest that this could be done. Pardon me?
How are you going to get it there? The delta V to get it, unbelievable.
Yeah. It
There's
depends
no
on
rocket in the world that can get it.
depends on the configuration of the orbit. Absolutely.
So it's
Yeah.
a big, it's not a simple problem.
No, it's not.
It's not something you could just instantly do something.
No,
about.
that's absolutely correct. You're absolutely right, Jim.
Question, yes.
On your near objects,
Mhm.
or outer,
Mhm.
you imply that their natural life history is they're going to extinct, most likely.
Mhm.
So they're going to collide and become smaller pieces which are less of a threat.
Right.
Do we have any idea if we have a steady state? Are new ones coming in?
That's a great question. That's a great question. If these things only live for or if these things only are near-Earth objects for 1 million years, why weren't they gone a long time ago? There's actually a lot of work, and it turns out, remember I referred to sunlight pressure pushing these things around? What happens, we believe, is the pressure of sunlight actually pushes main belt asteroids into areas called residence zones with Jupiter, where they are thrown out of their orbits. Think about pushing somebody on a swing. You know, if you push just a little bit at the right time each time, you can get somebody sailing way up high on a swing. That's what Jupiter does to these objects that are in the right areas, into these resonance areas. And if there is a mechanism that can continuously push objects into these resonance zones, it's those resonances that can throw the objects into the inner solar system. And there's been a lot of work done on that recently. We feel pretty comfortable that we understand how these things are getting refreshed.
There's a question here, yes.
I'm curious about the reason for your higher discovery rate than other groups. Is it more living time, big scale, what, all the above?
I think the numbers indicated it's probably something a little better than luck. I would say that the principal issue is we use human beings who look at the objects in real time. A lot of the surveys use automated systems to find the objects, and as a result, that limits how faint they can go. But there's nothing that can beat that human eye-brain combination. I mean, I can sit and look at one of these things when I'm observing, and I can tell you in half a second whether it's real or not. You know, we've just trained ourselves to look at these, and we can find them very faint, way down in the noise. Very difficult to write software to find stuff like that.
Now, the eye's very good. Most of you noticed that one you had up there that didn't have it marked.
Right, you can find it.
Very obvious very quickly that it was moving.
You bet. You
I'll
bet.
take 2 more questions. Here and then here, yes.
You were saying that with this group of observatories, it's covering the sky every month?
The observatories operate every night, just except around full moon typically.
But it takes a full month roughly to cover the entire sky.
Yeah, in the course of a full month, as long as everybody's got pretty good weather, we get the entire sky covered every month.
How is the LSST telescope that's being built going to change that?
It's going to walk away with the job. Basically, good question actually, because you probably have heard about the LSST. I'm not going to tell you a whole
There's
lot.
a big poster in our lobby.
Yeah, and the LSST is going to be a telescope we think probably built before the end of the next decade. We hope it gets built before the end of the next decade. In fact, here's a picture of it. The mirror is being made right now, being ground at the Mirror Lab. This telescope will cover the sky every 3 days. And it will just cover the sky about 4 magnitudes deeper than we do with our survey, which is about 10, 15 times fainter. It will take terabytes of data per night. And the thing that's going to be really cool about this telescope is all that data is going to be available for anybody to look at. It's really a people's telescope. So this thing is going to take data every night looking for change. So there's a lot of scientific rationale for having this telescope, but in the process of looking for interesting astrophysical phenomenon, it's going to sweep up pretty much everything in the solar system.
And our last question, yes.
Well, to follow up on that,
Uh-huh.
even people associated with both PAM-STARS, which is operating now, and LSST, claim that they will not be able to follow up on roughly 10% of the objects in the fund. They'll be finding zillions.
Zillions.
I'm wondering if that means that when these new surveys come along, will you just shut down completely, or will you start doing just follow-up of these new surveys?
We think that there's plenty to do. All those future surveys do have certain limitations because they're dual-use surveys. They're trying to do things of interesting scientific astrophysical interest as well as trying to find NEOs. And we believe that there are gaps that will be left through their observing strategies and in the follow-up, the job of actually looking at these objects after they're discovered, that probably will keep an important niche for amateurs as well as professional observatories like our own. So we believe that follow-up really is something that we could probably do pretty productively, even in the time of LSST and PAM-STARS, which are these advanced surveys.
All right, I'd like to remind you, our next slide